Okay, welcome back. Our second speaker is Professor Eilers from SVS Westtech GmbH. He works as a researcher and engineer, and he's an expert in the field of biophotonics. The title of his talk is Accessing the Nanoscale with MINFLUX Light Microscopy. Let's welcome Professor Eilers.
Yeah, thank you very much for the nice introduction. Today I'm going to talk about accessing the nanoscale with MINFLUX light microscopy, which was actually a work that was done at the Max Planck Institute of Multidisciplinary Sciences in the Department of Nanobiphotonics, which is headed by Stefan Hell. Is it working? I might have to do it like that. Yes. So different microscopy techniques have been around for a long time. Electron microscopes, for example, have been around for several decades, and they opened up resolution scales up down to the nanometer scale, which really helped a lot in cell biology. Nevertheless, scientists nowadays still use a lot light microscopes, especially fluorescent light microscopes, and that is because of its specificity and its compatibility with living cells. These light microscopes have a problem though, meaning that they allow only resolutions down to a couple of hundreds of nanometers. And that is because of the so-called diffraction limit of light that was found in 1873 by a German physicist called Ernst Abbe. And he found a formula that is carved in stone in Jena that basically states that the resolution that you can achieve is proportional to the wavelength of the light you use divided by the numerical aperture of the objective that you use. It took until 1946 where a first window to the nanoscale was found, and that was actually first a resonant energy transfer, but it was not until the 1990s that actually true super-resolution microscopy was found. And as you might know, this got the Nobel Prize in Chemistry in the year 2014 that was awarded to Eric Betzig, Stefan Hell, as well as William Murner. And even though theoretically unlimited, this resolution or this super resolution microscopy allowed to access now resolutions of about tens of nanometer with fluorescent microscopes. So when I was working in the group of Stefan, the question that we asked ourselves was, well, how far can we actually push these methods? And that's what the talk today is going to be about. But before I go there first, I would like to briefly show what is the diffraction limit of light. So if you take a microscope and you focus down a laser light, you will be able to achieve a Gaussian-shaped excitation spot if you want to, and you can focus it better and better the bigger the numerical aperture of the lens is that you use. And with the best microscope objectives that are available nowadays, you are able to focus down the light to a spot of about 250 nanometers in XY and about 500 nanometers in Z. So what is the problem here? Well, if you illuminate a sample where we have, for example, fluorescence emitters, you will illuminate multiple fluorescence emitters at the same time that you will not be able to separate. Fluorescence super resolution microscopy changed that, and once it was developed, it actually really took off and touched nearly every corner of cells. So there were a lot of experiments that were done for all kinds of different parts of cells, and these methods were improved upon over the years, over time, and now even give access to multicolor imaging and also to multicolor imaging in 3 dimensions, as you can see here on the right side. So over the years, there were a lot of different super resolution techniques that were developed, and you can basically separate them on the one hand in confocal methods or in wide field methods. And depending on your problem that you want to solve and your considerations, like for example, the spatial resolution, the time resolution, or the phototoxicity that you can allow in your sample, you would choose one or the other of these techniques. So I now want to focus on 2 of these techniques. On the one hand, a confocal method called stimulated emission depletion microscopy, and one wide field method called single molecule localization microscopy. So both of these methods rely on the on and off switching of fluorophores to achieve superresolution, to break the diffraction barrier. So if we look at STAT, here we have a classical excitation beam that is focused down to a Gaussian-shaped beam. And in backscattering geometry, we collect the fluorescent photons. And to break the diffraction barrier, we superimpose a STAT beam that is basically going to turn off all molecules except the one that are in the center. So if I look at an XY cut, what do I have? I have a green excitation laser that is going to activate a lot of fluorophores that basically emit light, and I have a red STAT beam that is going to turn off all molecules except the one that are in the center. And if I increase now the power of the STAT beam, I can reduce the region in which fluorophores are allowed to emit light, and I can achieve very, very high resolution. I can also look at an XY cut. So here you see that I have like the STAT beam superimposed on the excitation beam, and with that I'm able to separate emitters that are close together. Here in this case, the resolution has a dependence on, again, the wavelengths of light, as we already know it, the numerical aperture, and has a dependence on a term that depends on the intensity of the excitation light divided by the intensity of the STAT beam. In single molecule localization, on the other hand, I use a different approach. Here I have an excitation laser that is used in wide field, so I illuminate the whole sample at the same time, and the on-off switching is done by the fluorophores themselves. So I try to make sure that only one fluorophore is on a certain area of the camera to localize it to achieve a very high localization precision. So imagine that I have multiple emitters that blink, and I record them on a camera. I localize each respective emission that I get, and I can reconstruct the final image. Depending on the probes that I use to make them blink, these methods got different names. STORM, for example, for blinking dyes, PAWN for photoconvertible fluorescent proteins, or PAINT for exchangeable reporters. And all of them rely on the same idea that I measure on the camera my emission point spread function. I just estimate the localization of the molecule out of it, and it turns out that I get a resolution that is proportional to the wavelengths of the light divided by the numerical aperture of the lens times a term that depends on 1 over the square root of the total number of photons that I measured. So this is going to be important. We just learned, okay, the resolution is limited to a term also that is 1 over the total number of photons. Well, it turns out that for typical emitters that one uses to make these methods, the photon budget, so the amount of number of photons that I have access to, is limited. And this in turn also limits the precision that I have access to. Or you can also think about it a little bit differently. If you say that the total number of photons is nothing else than the count rate, the emission count rate, times a certain time resolution, then for a certain precision, I have a limit on the time resolution that is given. Now, there are different ways of optimizing that. One could, for example, use anti-bleaching agents, special fluorophores, cryogenic conditions to optimize that, but all of them also introduce certain drawbacks. So we didn't want to go that route. We didn't want to basically go in this way, but we said, can we do better with the amount of photons that we have? And that in turn led to the development of a new microscopy technique that we call MINFLUX. And that basically uses elements of the one hand of the wide field illumination and also of the confocal methods, and I'm going to show you how it works now. So for that, I'm going to first look at it in a one-dimensional case. So imagine that we have a single emitter, as we do in single molecule localization microscopy, and we are going to use a confocal excitation beam from the confocal world to excite it. So imagine we have a donut-shaped excitation beam with a 0, and here we are going to measure n1 photons. Then we are going to displace the beam in the next excitation, and we are going to measure n2 photons. So that means we now have 2 excitations that we use, where we measure n1 and n0 photons, n1 and n2 photons, and out of the relative ratio of the photons that we measure and the knowledge of the beam shapes, we can localize the emitter. This is easy to understand. So imagine that we have an emitter that is closer to the 0 here. Well, then we are going to measure less photons here and more photons here. Or on the other hand, if we are closer to the 0 here, we are going to measure less photons here and more photons here. So we can think of, on the one hand, the distance between the two displacements here, the distance between the zeros, as kind of a ruler. And we can think of the ruler divisions as the number of photons that we collect. So this is easy to understand. Imagine we have, for example, a total of 4 photons that we collect. Then, well, if we measure the combination 0 and 4, we are going to be here. If we measure 4 and 0, well, we are going to be here. And for combinations in between, we are going to be somewhere in between. Now, as it's done classically in statistics, we can just improve the localization precision by increasing the information, meaning the number of photons that we can use. So basically, we just increase the divisions, if you want to, and get a higher localization precision. But this is not the game that we are playing here. Remember, we want to be better with the number of photons that we have. So we are not going this route, but what we are going to do is just to say, well, if we have a ruler, let's just shrink the ruler. So we basically just shrink the ruler, shrink the distance between the zeros, and with that, we can increase the precision for the same number of photons. And this is basically the big trick that we play throughout this whole presentation, here simplifies in 1D, and that in the end allows us to get a better precision. So given this, meaning that from a perspective of the molecule, we try to use less photons, meaning to minimize the photon fluxes of emission for a good precision, we gave this method the name MINFLUX. Or if you think about it from an excitation point of view, we try to find an excitation scheme such that we have ideally a maximally informative luminescent excitation scheme. The distance between the zeros, which is going to play a crucial role in this presentation, is going to be called L. Okay, so now we understood the method from a conceptual point of view. Now I would like to include a little bit like a mathematical formulation of it. So in the first measurement, we are going to measure N0 photons, where these N0 photons are going to follow a Poissonian distribution, where the mean of that Poissonian is going to be proportional to the intensity that the molecule sees. In my next excitation, I'm going to shift the beam by a distance L, and in this case, I'm going to measure N1 photons, where N1 follows a Poissonian, where the mean of that Poissonian is proportional to the intensity that the molecule sees at this position. So, as I already said at the beginning, out of the relative ratio of the photons, I can localize the emitter. So I can define a so-called success probability that is nothing else than the ratio of N0 divided by the total number of photons, or if you write it differently, it's the intensity of the zeros beam divided by the total intensity, and this is going to be my success probability P. I can look at how this P function looks. Well, if we are at the 0 of my zeros excitation, I'm going to have a 0% probability of measuring photons here and a 100% probability of measuring photons here. So that means my P function is going to take on a value of 0. Here, on the other hand, I'm going to have a 100% probability of measuring all photons here and a 0% probability of measuring photons here, meaning my P function is going to take on a value of 1. And for the area in between, well, my P function is going to be something in between. Meaning, if I measure, for example, 100 photons, where I measure 60 and 40 photons, so 60 divided by 100 is 0.6, the problem that I need to solve now is nothing else than, well, at which x position does my P function take on the value of 0.6 to localize the emitter? Well, I can do that. I just take 0.6, project it on my success probability function, and there we go. I have the molecule position. Now, we know that my photons are going to fluctuate following a Poissonian distributions, so this p-value that we measure, this relative number of photons, is fluctuating too. And actually it turns out that if I make a constraint for a certain number of total photons, so if I fix these total numbers of photons, then this p-value is going to fluctuate following a binomial distribution. So I can go ahead and plot this binomial distribution here, and you can already imagine that this will give rise to an uncertainty in the position estimation. So I just take my binomial distribution, project it on my P function, and there we go, we have our localization uncertainty for this method. Now the big question that arises is, well, how big is this localization precision? So to do that, so we want to know how big is this localization precision. So to do that, we can use information theory, and we can just use the Cramer-Rao bound, meaning what is the best possible localization precision that I can achieve with any unbiased estimator, which is the Cramer-Rao bound. This Cramer-Rao bound can be calculated using the Fisher information, for which I need the likelihood function that is known, given that I have a binomial. And I can go ahead and calculate it for my excitation geometry that I use here. And it turns out that it takes on a very, very simple functional form, especially if I use a quadratic approximation of my donut-shaped beam around the origin, where the donut-shaped beam can be approximated by a parabola. Then I get just this simple functional form that gets even simpler if I look at it at the origin, meaning here in the center at 0, I retrieve a simple function that is just 1 over square root of n, so the number of photons, times L divided by 4. And this is a striking result. Why is that? Well, look at the other methods up until now. All other methods had to depend on the wavelength and on the numerical aperture of my lens. This completely vanishes in our case. We have no dependence on the wavelength, we have no dependence on the numerical aperture of the lens. We only have the dependence of 1 over the square root of the number of photons. And we have a geometrical parameter L that we can tune to our liking to improve the localization precision. So that means this is basically this ruler size that I introduced at the beginning. So I can make this ruler smaller, and if I make the ruler smaller, well, my probability function, my p function gets steeper, and if I project my binomial distribution on top on this steeper p function, well, I get a better localization precision. Furthermore, we see, okay, there's a drawback. The drawback is we don't have a constant localization precision as a function of x. This can be seen here. We have actually a dependence on x squares, so it grows with distance to the center of our ruler, basically, if you want. How can we make sure that a molecule sees, or that we measure the same number of photons if we make the zeros closer together? Well, the easy answer is, given that we are dealing with zeros, it's actually quite easy. We just make the zeros of our donut closer together, we increase the beam power, and then we can make sure that the molecule still sees the same relative intensities and that we still get the same number of photons for our measurements. All right, so this was MINFLUX in 1 dimension, but we want to make 2-dimensional measurements, MINFLUX in 2D. And now I want to show you how we can achieve that. So for that, we went ahead and built actually a microscope, so basically a confocal microscope that is focused down to, in this case, a Gaussian-shaped beam first. We add in backscattering geometry detection to detect the fluorescent light. We add a phase mask to create a zero that we know that we need, so a donut-shaped beam, and we know that we need to displace this donut-shaped beam. So, well, we make an XY beam deflector and an FPGA board to control all of that. And there we go, we have our microscope. So if we wanted to image an emitter, here you see 9 emitters. The first thing we have to realize is, well, we need to make sure that each molecule needs to be localized one at a time. So only one of them is allowed to be on. If we had a camera, yeah, we would get this big distribution. We would basically localize it using the center of mass or some other estimation of position, but we don't care about that. We just care about the total number of photons that we measure for our excitation, and we are going to measure as such. We are going to start with a central exposure, followed by 3 peripheral exposures that are on a circle with distance L. So basically what that means is we start with the central donut exposure, we measure N0 photons, we make our first peripheral excitation, our second, and our third, where we basically measure N1, N2, and N3, so we have 4 photon counts, and out of these 4 relative photon counts, we can localize our emitter. So how good are we with this method? Well, we can look at the localization precision as a function of the number of photons that we collect. And here in black, you see the Cramer-Rao bound of an idealized camera localization. And in the dashed lines, you have the Cramer-Rao bound of an idealized camera localization with a realistic signal to background ratio. And if we superimpose our results, you see that it's the center of our origin. We are better than a camera for the same number of photons. And actually, we are better, in this case, for an L of 50 nanometer by a factor of 5 in the localization precision. Or if you want to think about it differently, for the same error, for the same localization precision, we need 20 times less photons with this L. This L is tunable. so we can change the L value if you want to. So we have bigger field of use at the drawback of lower localization precision. This is a game we can play. We can also look at, well, what is the localization precision as a function of the L value? And as you imagine from this formula, the smaller L gets, the better our localization precision is. And in the case of no background contributions, L can basically be made as small as we want to, and we get better and better and better and better and better. But in reality, we are going to be faced with background contributions. So that means that if we introduce background, the localization precision is going to get worse as we expected. And additionally, there is a minimal L that is introduced that makes sense to use. And if we make L smaller than this minimal L, well, then the localization precision gets bigger again. How is the XY dependence of this method? Well, if we look at the localization precision map in XY for different Ls from 125 nanometers to 50 nanometers, we see that also in 2 dimensions it's it's a changing localization precision with X and Y. We can look at an XY cut and we retrieve the known functional forms that we know, that it gets better and better and better with smaller L, but it grows more or less quadratically away from the origin. We can also look at the covariances, and we see that the localization precision is actually anisotropic in our field of view. So, in summary, we now have a method that is independent of the wavelengths and independent of the numerical aperture, that is not based only on photophysical saturation to increase the localization precision, but we have access to a geometrical parameter that allows us to tune the spatial-temporal resolution of our experiments. Okay, what can we do with such a method? We devised 3 applications at the beginning. On the one hand, that would be classical nanoscopy, meaning that we would just localize emitters inside of our field of view. So we would make them blink, and whenever an emitter turns on, we would collect our relative 4 photon numbers and localize the emitter with that. Another application is short-range tracking, where basically we have an emitter that moves inside of our field of view, and depending on the relative photon numbers, we would localize it again. Or alternatively, we can also use a long-range tracking application where we follow an emitter with our excitation beam pattern, ideally having it always centered, such that the central count rate that we have is minimized and the one from the peripheral exposures is about constant. Okay, so now we know how this method works in theory. We have a microscope. We can basically start, except that we don't have an estimator yet to localize the positions in reality. And for that, we evaluated a maximum likelihood estimation scheme at the beginning. What does that mean? Well, in order to have a maximum likelihood estimator, we need a likelihood function. And in order to have a likelihood function, we first need our success probabilities. Then in case of 4 beams, it's nothing else than the intensity of the ith beam divided by the sum of the total intensity for my ith success probability. And here you see how the success probability looks for my 4 different beams, meaning the central one, the first, the second, and the third peripheral exposure. As I said, for a maximum likelihood estimation, we need the likelihood function. The likelihood function typically use the log likelihood function, which is what we do here too. And it is for a multinomial. So remember, in 1D we had a binomial. Here we just have a multinomial. It's nothing else than the number of photons of the zeros exposures times the logarithm of p0 plus the number of the first, the number of photons from the first exposure times the logarithm of p1 and so on. And to localize the molecule, what we have to do is nothing else than to calculate these likelihood functions for the 4 number of photons that we measure, look at the maximum of it, and there we go. We have the molecule position. So now we have a maximum likelihood as an estimator that we know from theory that it is unbiased and that it is asymptotically optimal, meaning that it converges to the Cramer-Rao bound. It is not really a fast estimator. This is perhaps a bit of a drawback. And experimentally, we found that yes, it is unbiased, yes, it is optimal, but only for above 150 photons. Remember, we devised 3 different applications. For imaging, yes, this maximum likelihood estimator might be fine, given that we have a lot of photons here probably per event, but especially for this long-range tracking application, we might be faced with little number of photons per localization, and actually the requirement of a very, very, very fast estimator. So for that, we went ahead and devised a least mean square estimator, which is nothing else, honestly speaking, than a heuristic estimator, so a very simple functional form that can be approximated by just requiring that the relative number of photons equals our success probability function approximated around the origin. Then we retrieve a simple functional form that we change slightly to also include the radial scaling of our central exposure, and we get this form which is dependent on parameters k and beta that we just can choose to our liking. This estimator, as you can imagine, it's not unbiased, it's not optimal, but it is super fast and can be calculated in an FPGA in a very, very short time. If we do and we use this estimator, we still want to know where was the molecule in reality. And given that this is a closed functional form, we can just unbias this in post-processing. So we can devise a numerical unbiased version of this estimator, which we did, and which turns out to be unbiased, that turns out to be optimal, especially in a small field of view around the origin, so in our field of view here. And this is true for even low number photons of 10 photons. But it is super slow, so this is the drawback of this estimator. So now we have a maximum likelihood estimator for imaging, we have a least mean square estimator for tracking and live estimation, and one for post-processing in the case of low signal numbers. So now we can go ahead, but before we do so, you might ask the question, why do you actually use 4 and not 3 beams for XY localization? And you might be right. With three exposures, I have enough information to localize the molecule in 2 dimensions. But if I look at, for example, the likelihood function here for 26 photons, where we measured in this case 6, 8, and 12 photons on our 3 exposures, the likelihood function takes on a very not nice form. It's not well behaved. As you can see, it has more or less 3 maxima. Remember, maximum likelihood means I want to find the maximum of this function to localize the molecule, which is not nice in this case. But if I use 4 exposures, meaning a central one, for the same number of photons, n26, and the same realization of photons as here, so 6, 8, and 12, with the only difference that I have 0 photons from my central exposure, well, I get a way better behaved likelihood function, which is a clear maximum. So this is a good example that collecting 0 photons is actually highly informative. Okay, now we have everything together to do the applications, and we started with the tracking applications. So for that, we reached out to the Uppsala University, to Johan Elf and Arvid Ginner, who provided us with bacteria, with E. coli, where the ribosomal subunit was labeled with the photoactive fluorescent protein, MES2, and we went ahead and tracked it with our method. So here, we used the fast live position estimator, and we had to be a bit careful given that this protein is actually blinking, so it's on and off, with on-time scales of 2.2 milliseconds and off-time scales of 0.6 milliseconds. And well, we had to take all that into account, also the diffusion, the blinking, and the brightness of this emitter to tune our tracking parameters, meaning the live position estimator, the beam separation L, as well as the pattern repositioning rate. And well, we went ahead and tracked, and it actually worked. So here you can see the number of localizations that we were able to track inside of the bacteria, as well as the time resolution. And in our case, we used the time resolution of only 125 microseconds per localization. We repeated that for a lot of different ribosomal subunits, and here you see all the traces that we achieved. And it turns out that on average, we got about 742 localizations per trace, which is about a factor of 100 times improvement over typical camera localization schemes that were used at that time with this emitter. And our time resolution is also considerably better than the one that was typically present for camera localizations. Here you see the count rate, where indeed the central exposure that is shown in blue is lower than the peripheral exposures. Here you have the corrected XY trace, out of which we can now estimate the diffusion coefficient of our ribosomal subunits. And in this case, we see, for example, that we can see multiple diffusion states that were present. We can also go ahead and look at the mean square displacement curve for our trace. And if we actually fit this mean square displacement curve with just the least mean square fit, we can retrieve the value at the origin, which will give us information about the tracking error. So we see that in our case, for an average of only 9 photons, we retrieved a localization tracking error of 50 nanometer, which comprises a 5 to 10 times improvement in photon efficiency as compared to the idealized camera performance. After that, we went on and decided to tackle nanoscopy, so imaging basically, where we devised an origami sample with ATO647 emitters that are only 12 and 11 nanometers apart. We made them blink and we localized them with our method. So here you see the blinking of the single emitters. We collected the relative photon numbers for them and we went ahead and localized them. Here you see the localizations that we retrieved for n higher than 500 photons per localization. And if we make a histogram out of it, well, you see that we can retrieve the origami sample as we expected to. We can also look at the localization precision that we retrieved, and we can see that now we actually accessed the nanoscale of about 1 nanometers using only about n500 photons and higher. Repeated that for a lot of different origamis, actually even for a smaller origami where the distance between the molecules was only 6 and 5 nanometers, and here you see the histogram as well as the single localizations, and if we look at the localization precision, that was again 1 nanometers, we were able to separate emitters that are only 6 nanometers apart with that method. So this basically concludes the first paper that we published, which was, as I said, done in the group of Stefan Hell and Francisco Balzarotti, Klaus Gross, and myself worked on MINFLUX. Volker Westphal supported us, and we collaborated with Arvid, Johan, and also Fernando Stefani. But we didn't stop there. We continued to work on the method afterwards. And the first thing that we did was to access this, well, let's call it short-range tracking. So what we did here. First, we defined a region of interest, which is the red region here, in which we want to operate. And we tried to find a value L, so a circle diameter if you want to, where the localization is in average minimized inside of this red region. So this we can calculate. So if we look at the region of interest as a function of the optimal L parameter, we get for no background a certain kind of relationship. With background, this relationship is a little bit different. And we decided to opt for a region of interest of about 30 nanometers, which gave us an L value of about 50 nanometers. We tried to operate with about 2 to 3 nanometers localization precision. That was our goal. So we see here in blue, this is the localization precision that we can achieve. So 2 to 3 nanometers can be achieved with about 100 photons, which we opted for. Depending on the count rate of the emitter that we use, well, we can also look at the localization precision as a function of the time resolution for a given count rate. And it turns out that this 2 to 3 nanometer resolution can be achieved if we use a time scale of about 400 microseconds. So this is what we opted for. We went ahead, used an immobilized ATO647 emitter, and for an average of 138 photons, we retrieved a 2.4 nanometer localization precision at a time resolution of 400 microseconds, which is a 17-fold improvement of the photons needed as compared to an idealized camera localization. And actually for this emitter, this 2.5 nanometer was unreachable with the typical camera localization just because this emitter would not be bright enough to emit enough photons in 400 microseconds. The next experiments we did was to build an origami bridge, where we basically have an emitter that is allowed to move only in one dimension on the length scales of about 20 nanometers. And we went ahead and tracked also that with our experiment, with our setup. Here you see the photon counts. Here you see the X and Y traces that we retrieved, and we can actually zoom in onto it. I don't know if it's easy to see on a small region here, which is this region. And there you can see that indeed the molecule stayed at these two positions for a while. And we can also retrieve the movement of the molecule between these positions with a pretty high time resolution in our case. And we even see that we can see that this one-dimensional movement really was there. Okay, biologists now might say, well, this is pretty cool, but I don't care. I want large field of view. I want to work in cells. I want 3 dimensions. And I want multicolor imaging. Okay, very nice. This was a part where I basically finished my work in the group of Stefan, but Francisco, Balcerotti, Klaus, as well as Yasmin, who joined the group, continued to working on extending the field of view of MINFLUX. Remember, in our case, currently, we just have a small region where we can work, and if we have an activation laser to activate a single emitter, it might be, I don't know, in places where we don't get a very good localization precision. So many molecules are not going to be localized efficiently. To solve that problem, what we can do is first make a coarse localization, where we use, for example, 4 Gaussian excitation beams to get a coarse localization of the emitter, and then superimpose our MINFLUX scheme on top of the emitter. And then what we're going to do is that we just zoom in on it, basically make our L smaller and smaller so that we ideally perfectly centered on the emitter and squeeze out as many photons as possible to localize it as precisely as possible. This can be done for every emitter that pops up, and basically like that we can have access to a large field of view with high photon efficiency everywhere. And there's a little surprise that was shown too. It turns out that if we use this scheme and we look at the localization error of the function of the total number of photons for this excitation scheme, where we first start with, let's say, coarse Gaussian localizations, and then we turn on our MINFLUX and start with an L of 150 down to 30 nanometer with 4 steps. Well, if we look at our error dependence at the total number of photons, it's not scaling with 1 over square root of n anymore. It's not scaling with 1 over n neither. It starts to scale with 1 over n squared, which was a pretty cool finding, I think. So this was used for fixed cells where nuclear pore complexes were labeled with Alexa Fluor 647. So basically we scanned, or they scanned with an activation laser, and whenever a molecule popped up, one would zoom in on it with the MINFLUX scheme. So here there is a function as a function of time. You see here different events, where here a molecule popped up in a very, very, very short time. One zooms in on it, one squeezes out the photons with a very, very small L and localizes it. And this is repeated for every molecule that pops up. With that, one could nicely retrieve the circular geometry of these nuclear pore complexes. And actually, if we look at the localization precision, in this case, one got in a fixed cell a median localization precision of only 1 nanometers. This experiment was repeated for a different emitter. So in this case, one used a photoconvertible protein maple. And also here, one could retrieve the circular geometry and actually got a median localization precision of 2.3 nanometers. This was even done in living cells, giving rise to MINFLUX on large field of view in live bacteria, or sorry, in live cells in this case, which also worked quite nicely. The next thing that was done was to extend the methods to 3 dimensions. Remember, currently we only work in 2 dimensions with a donut-shaped beam, but we can also use a top-hat beam that looks a little bit different, that has a central zero that grows in Z and grows in XY. And here we can use a simple, slightly different excitation scheme, where we have basically 5 exposures in XY, an additional 2 exposures in Z, so that we have access to a localization precision that is going to be dependent on the diameter L in XY, which is going to give localization precision in XY, Lxy divided by square root of n. And at the same time, we also have the spread in Z, which is going to give rise to a localization precision of Lz divided by the total number of photons. So how can this be done? Well, we first start with, again, our 4 Gaussian beams to localize the molecule coarsely. Then we turn on our top hat beam, and we make 2 measurements in Z, then make the measurements in XY, and again, iteratively zoom in to localize every single emitter. So this now gives access to a method where we have 1 over n square scaling for the XY localization precision, and also in 1 over n square scaling for the Z precision. This was done again for nuclear pore complexes in fixed cells, and we can see that we could retrieve basically 3D images where we even can separate the upper and the lower part of these nuclear pore complexes with this method. The localization precision here was about 2.6 nanometers in XY and actually 1.75 nanometers in Z. So suddenly we have a method where we have nanometric isotropic resolution in 3 dimensions with a single objective length. The last thing that was done that I want to talk today about is multicolor imaging. So here, what was done was to include a beam splitter in the detection channel so that different molecule families could just be separated in these detection channels. So how does that work? Well, we make the molecules blink. We collect our N or 4 photon numbers for localizations, but we can also look on these 2 detectors, and depending on the relative ratio of the counts on the 2 detectors, we can classify the molecules to belong to A or B. So as a proof of concept, an origami was divided with 2 different families of emitters, spectrally shifted. Here you see the histogram of localizations, and if we include the spectral shift here, well, we can just attribute it to different molecular families, and there we go, we retrieve the origami as we expected to. This was then extended again to fixed cells where the center of nuclear pore complexes was labeled with a different color, and this enabled multicolor imaging in 3D with MINFLUX on large field of use. So in summary, we have a scheme that is now independent of the wavelength, independent of the numerical aperture. We introduce a parameter L that we can tune to our liking. The localization precision is going to be proportional to that parameter L divided by n to the power of k over 2, where k is nothing else than the iteration steps that we use. So for 4 iterations, we retrieve L over n squared. We have a tunable parameter so that we can tune our spatial resolution and our field of view to our liking. And that we used to track ribosomal subunits with 50 nanometers at 125 microseconds using only 10 photons for localization in living bacteria. We retrieved 2 nanometer precision at the time scale of 400 microseconds using only 100 photons per localization. We were able to get 1 nanometer localization precision using more than 500 photons per localization in multicolor. And we were able to extend these methods to large field of view, opening up nanometer resolution on large fields of view, even in living cells, and also give access to 3D localization with isotropic resolution everywhere in multicolor. This whole MINFLUX scheme was then commercialized actually by a spin-off of the Department of Nanobiophotonics, Bavaria Instruments, so one can actually buy these microscopes. And I have to make a disclaimer, so people that worked on MINFLUX actually hold patents. This is perhaps important to say. And finally, I want to end with showing an overview of all people that actually contributed. So the one with the green backgrounds are the one that worked on the MINFLUX itself. And we had collaborations of all these people that helped a lot and that we're really thankful about. Yeah, and this concludes my talk. So thank you very much for your attention.
Thank you, Professor Eilers. Any questions?
You're mentioning the probability distribution. So how many measurements do you typically have to take to get the distribution? Because that's when we'll decide the accuracy.
So let me try to see if I understood your question correctly. So if we go to, for example, let's go to this slide. Yeah, perfect. So you mean how many measurements did we take here to actually be able to define a localization precision, right?
For each point, you measure 4 points.
Yes.
Yeah, and each point you need to get a probability distribution. Yeah, that if I understand correctly.
So what we do for localization, right? So that is actually the maximum likelihood estimator. So let me try to explain it like that. So we multiplex these 4 positions really, really, really quickly. Very, very, very quickly. And we measure a lot of ratios N0, N1, N2, and N3, right? A lot of ratios because we multiplex so quickly. Then we sum all these photons up, So we get 1 and 0 value, 1 and 2 value, 1 and 3 value, and 1 and 4 value. So we have 1 n value for each exposure. And then what we do is we go to our maximum likelihood estimator, which is this one here. Zack. Where we basically plug these n values that we measured in here. We know our probability functions p because we measured the beam shapes in advance, right? So we know these p functions, so we can go ahead and calculate our likelihood function. And this likelihood function, basically, depending on the number of photons that we measure, will look like this. And then we just find the maximum. This is how we localize. But this is one localization only, right? And then we repeat that for different emitters and whatever, and we do this whole step again and again. And this is how we can localize with this method. Did I answer your question? Okay.
Okay, next question.
Hi, thank you very much for this very nice talk. I'll start by asking you to probably like elaborate on the relationship of the I guess the spatial resolution, right? For a super resolution microscopy, it's still a little bit surprising to know that is lambda independent, NA independent. I mean, if I follow this how to say like formula, does this mean that if I don't use a 1.4 NA objective lens, I can still get super resolution? I think there's still some like technical limitations or prerequisite, right?
Yes.
So this is surprising. So could you please elaborate on this?
Yes, absolutely. So let me start by saying what could be theoretically possible and what would be realistic in an experimental setup might be two different things. So in an experimental setup, I want to make sure that I have enough excitation light, that I have a true zero, and to be able to have, like, on the one hand, my true zero, a beam shape that basically has a growing intensity profile around the zero, to localize my single emitters. And if I don't really use a very, very high numerical objective lens, well, I might need a lot of beam power to actually create this, this enough intensity away from my zero to really excite the emitter with enough light, right? So imagine that I have a low magnification lens and I have perhaps a beam that is like, I don't know, 100 times bigger than actually the molecule that I want to localize. Then I need incredibly amounts of power to actually create enough differences in my intensity profile to get, to get enough signal, basically, right? So I think this is probably the experimental problem. But in theory, yes, in theory I can use no lens at all. And somehow, if I find a method to actually create, let's say, a donut-shaped beam without a lens, I don't know if that is possible. This is something that I'm not going to comment on, but if that should be possible, then yes, theoretically yes. But there are going to be experimental restrictions, let's say.
I have a follow-up question on your application about tracking.
Mm-hmm.
So besides the number of photons,
mm-hmm.
Would the ultimate tracking accuracy, be also depend upon the movement of the object itself?
Very good question. Yes, yeah. It is indeed. Yes, it is indeed. Because it's always a relationship between how much does the molecule move inside of my field of view when I localize it, right? So basically, if it moves too much, I will probably just have a very bad localization precision, right? So that means, in other words, I need to tune the frequency with which I update my positions to follow the emitter with the movement of the molecule. So this means the whole optimization of a tracking experience will be an iterative process. It will first be some first experiments to have an idea, well, what kind of diffusion coefficients am I working with? Am I working with fast molecules or am I working with very slow molecules? And depending on this first knowledge, I can optimize my tracking parameters and my repositioning rate to ideally make sure that the movement of the molecule away from this good region in which I can work is as small as I want it to be, basically, right? So yes, there is a trade-off, and this is in a sense also a limitation of the method. And it's a very good question, I think.
Thank you very much.
Thank you. Due to time limit, let's end here. Thank you, Professor Eilers.
Thank you very much.
Now we can take a short break for about 10 minutes.